We're now going to look at exponential functions. Exponential functions are ones in which the variable, the x, is in the exponent. In this case, the b stands for the base. See the difference between comparing f of x equals 2 to the x and g of x equals x squared, which is the kind of function we've normally been dealing with. F of 5, 2 to the 5th, gives us 32. G of 5, 5 squared, gives us 25. Because x is an exponent, negative values of x result in fractions. Remember that when x equals -1, as an exponent, that's the same as saying 1 over, so 2 to the -1 is 1/2. Anything to the 0 power is 1. Now, there's also what's called the natural exponent function, exponential function, which is f of x equals e to the x. The number e is like pi. It's irrational. It never ends. It never repeats. To a few digits, e equals 2.71828. Exponential functions deal with things like growth and, say, radioactive decay. We can graph exponential functions by completing t-charts. Now, a way to solve exponential equations is by making both sides of the equation have the same base. So remember that the base is not the exponent part, it's the other part. So here we have 2 to the 2x minus 1. Over here we have 32, which every number, if there is no exponent, has an exponent of 1. So this would be like 32 to the 1. The base would be 32. However, note from up above, 2 to the 5th equals 32. So now we have 32 written as base 2 with an exponent of 5. We can now set those two things to each other. And so here we have 2 to the 2x minus 1 equals 2 to the 5, which allows us then to make the exponents equal. In other words, we're going to have 2x minus 1 equals 5. And it's not so much that we have done an operation on them, it's that the only way these two sides can be equal, the only way that 2 to the 2x minus 1 equals 2 to the 5th can be true, since they both have the same base, is they both have to have equal exponents. And so now we can solve 2x minus 1 equals 5, leads to 2x equals 6, or x equals 3. And of course, if we were to plug 3 in for x, we would get 2 to the times 3, that's 6, 6 minus 1, that's 5, 2 to the 5th equals 2 to the 5th. Alright, so let's first evaluate a couple of functions. This one here is 3 to the x, and g is 0.5 to the x. So those would be exponential functions. So first find f of 0. So f of 0 is going to be 3 to the 0, and anything to the 0 power is just 1. In the second one, we want to do g to the -4. So g to the -4, well, that's going to equal 0.5 to the -4. Remember that the negative sign means the reciprocal of what's here. This is 1/2, so the reciprocal of 1/2 is 2. So that becomes 2 to the 4th. Please note that now we don't have the negative sign because I've used the reciprocal, and 2 to the 4th equals 16. Alright, so we're going to graph a couple of functions, exponential functions, see what they look like. So let's first do this f of x. 3 to the x plus 4, subtract 9. Again, we're going to make a t-chart. X, y, so that we can then graph it. I'm going to start at -4. You might wonder why I started there. Well, -4 plus 4, that'll make the exponent part 0, which then 3 to the 0 is 1. 1 minus 9 gives me -8. Okay, and I'll proceed from there. -3, so -3 plus 4, that's 1. 3 to the 1 is 3. 3 minus 9 is -6. -2. So -2 plus 4, that's 2. 3 squared, that's 9. 9 minus 9 is 0. -1. That's -1 plus 4 is 3. 3 cubed, 27. 27. Subtract 9 is 18. So one of the things to note is how fast this is going to grow. If I were to go to 0, by the way, we would have 0 plus 4, which is 4. 3 to the 4th, which is 81. 81 minus 9 is 72. Now, if I want to look at numbers less than -4, so for instance, -5, so that would be 3 to the -5 plus 4, which would be -1. 3 to the -1 is 1/3. 1/3 minus 9 would be -8 and 2/3. At -6, so -6 plus 4 is -2. 3 to the -2 would be 1/9. 1/9 minus 9 would be -8 and 8/9. And likewise, -7 is going to give me -8. And let's see. So that's -3, that's -27, so that's -8 and 26/27. I did that instead of decimal form just so that you could kind of see the pattern there. Alright, so let's go ahead and graph these values. So we have -4, -8, so -4, -8 would be right here. -3, -6. -2 is 0. -1 is 18. So that gets us up here. And of course, 0 would be way off the graph. -5 is -8 and 2/3. So that's going to be about right there. And then -6 is -8 and 8/9. So we're even closer, and of course closer as we go along. So our graph essentially looks like this, and then we're going to go up that way. And so, and of course, it will get closer and closer to -9 as we go along. In fact, in the limit, this part here gets smaller and smaller, so it'd be practically 0, and so we'd end up just with our -9. Alright, for the second one, let's go ahead and make a t-chart for this one as well. 2 to the 1 minus x over -8. And again, t-charts are nice because you can use t-charts on any function, and really the idea is simple. You just plug in your value and you go from there. So if I start with x is 1, 1 minus 1 is 0, so 2 to the 0 is 1, 1 minus 8 is -7. Now I put in, let's see, if I put in a -1, so 1 subtract the -1 is 1 plus 1, so that's 2. 2 squared is 4. 4 minus 8 is -4. Put in a 0. 1 minus 0 is 1, so 2 to the 1. 2 minus 8 gives me a negative 6. Let's see, negative 2. So that's 1 subtracting negative 2. That's 1 plus 2. That's 3. 2. Oh, so that'll give me 0. 8 minus 8. Put in a negative 3. So again, 1 subtract a negative 3. So 1 plus 3. That's 4. 2 to the 4th is 16. 16 subtract 8 is 8. Negative 4. So that's going to be 1 subtract a negative 4. So 1 plus 4 is 5. 2 to the 5th, that's 32. 32 subtract 8 is 24. And so we're now starting to get quite large. Just a few more values. Let's get to where we now have negative exponents. So in this case, if I made x2, then I'd have 1 subtract 2, which is negative 1, which would be a half. Half subtract 8 would be basically negative 7.5. And put in a 3. 1 subtract 3 is negative 2, which 2 to the negative 2 is 1/4. 1/4 subtract 8 is negative 7 3/4. 4 gives me negative 3 for the exponent. 2 to the negative 3 is 1/8. 1/8 subtract 8 is negative 7 7/8. And so you can see how the bigger x gets, the closer and closer I will get to negative 8. So let's go ahead and graph these. 1 is negative 7, so 1, negative 7. Negative 1 was negative 4, so that would be about right here. Negative 1, negative 4. 0 was negative 6, so that's there. The negative 2 is 0, so that's going to go through that as well. Negative 3 is 8, so negative 3 is up here. And negative 4 is 24, so that'll be well off our graph. Be like, let's see, 1, 2, 3, 4, be pretty close to up there. And then in the other direction, 2 is 7.5, so that'd be about right there. And then 7 3/4, and then 7 7/8, and so forth. So this one is going to get very close to negative 8, and then proceed from there upward. And so there we have the graph for the second one. The thing to note about both these graphs is how similar they look, even though at first blush they look very different. The extra numbers, the +4, the -9, the 1 minus x, the -8, that sort of sets the boundaries for where the graph is going to kind of bottom out. But in both these cases, we ended up with functions that look relatively the same. They're flipped, and the reason for the flipping is this one had 1 minus x, or this one had a plus x, and so that's why they're flipped. We could also flip them upside down if the base, in this case like the 2 here, was a -2 instead of a +2, in which case then the exponent would drive it more and more negative. But the shape is pretty much always going to be the same thing. All right, let's look at a couple of examples of changing base to solve a problem. In this first one, we have 9 to the 2x plus 3 equals 81. Well, I can rewrite that as 9 to the 2x plus 3 equals 9 squared. 81 is 9 squared. Now that my bases are the same, the only way that this can be true is if the exponents also are equal. And so now I have 2x plus 3 equals 2. So 2x equals negative 1. And therefore x equals negative 1/2. And so I have solved that exponential equation. Okay, here, same thing. On the one side, I got 2 to the 4x plus 14. Over here, again, you're not necessarily going to know what 1024 is in terms of 2 to some power, but we're trying to make the basis the same. And so one thing to note, this is 1 over. So I'm going to end up with a negative for my exponent. And then, if you don't know, you can simply play with the calculator a little bit to find out that, in fact, 1024 is 2 to the 10th. And so 1 over 1024 is 2 to the negative 10. And so, like the previous problem, I can go ahead and set these equal to each other. Move the 14. Divide both sides by the 4. And then I have solved that one as well. And so we have where we can solve equations by making their basis the same. All right, let's look at a couple of problems in which we use exponential functions. The first might be familiar to some of you if you've done any business classes. This is the formula for basically having interest payments or interest-bearing savings account. The P is the principal that you started off with. A is how much is in the account after a certain amount of time. R is the interest rate compounded n times per year. So for instance, if it's compounded monthly, then it's 12 times per year. If it was compounded daily, that would be 365 days per year, and so forth. And the T is after how many years. So suppose you deposit $500 with an annual interest rate of 2.5%, compounded monthly. How much money would you have after 5 years? So plugging these numbers in, basically we're going to have A of 5. Remember, that's the T, 5 years. So we started with $500. 1 plus, the interest rate is 2.5%, which we have to write as a decimal. And then it's going to be compounded monthly, so that's 12 times per year. And then the exponent part, n 12 times the 5. And so this is what it would look like with all the numbers plugged in. So I have the 500 that I started with. 0.025 over 12 is 0.0021, so this part. And then 12 times the 5, that gives me 60. Now, on my calculator, if I want to do something like that, what I can look at is the hat button, which is right here, to do exponents higher than that. So let's go ahead and turn this on. Maybe put on a little light to help kind of, no, that's a little bit, that won't work. But basically, I want to do 1.0021. Then I do my little hat symbol. So notice how the hat symbol comes up on the screen. I think I have the right number of zeros. Yes. And then we're going to do our 60. So there's what it would look like on the calculator. That's a way that I can do exponents. And the nice thing about the little hat symbol is that it also allows me to do fractional exponents as well. So I just put them inside a parenthesis or use a decimal for that. So go ahead and do that, and I get that 1.0021 to the 60th power is 1.134. So we're going to have 500 times 1.134, and we can go ahead and multiply, and we come out with $567.06. Actually, it'd be 7 cents, but we can leave it there. Now, one thing I might mention is that if you over round parts like this or parts like that before you do your exponents, you could get off a little bit in your answer. It's better to just let the calculator carry as many digits as it can. You don't have to write them all out, but let the calculator carry them. So, I actually had an answer that was 1.134132322. I don't need to write all that down, but I could go ahead and leave it in the calculator and then go times my 500 to get the 567.06. By the way, this would also show you that after 5 years, my $500 is making $67.06. So could take a while for that savings account to really produce, much longer than 5 years. There is generally a rule of 70 that you can use, in which you take 70 and divide it by the interest rate. So 70 divided by the 2.5 gives me 28. So basically it would take 28 years approximately to double my 500 to 1,000. And in fact, we can check that real quick. If I go, let's see, the 1.0021 to the, now this was for 5 years, so if I go 28 years, that would be 12 times 28, so it would look like that, and hit that, and I come out with 2.023, and so times my 500, I get 1,011. So my $500 became just over $1,000, but it took 28 years to do that. Now, of course, it will keep growing and growing, just as you can see in the graphs. But when you're down at this part of the graph, it takes a really long time to start going. All right, so as I mentioned, exponential functions can be used for growth and decay problems. Growth is usually done with something like population. So let's look at the second example here. The population of a particular small town can be approximated by the function f of x equals 75,000 e to the 0.018t, where t represents the number of years after 1984. So I would assume then in 1984, t would be 0. So all of this part would just be a 1. Our population was about 75,000 in 1984. So the question is, if that's the function of growth, what will the population be in the year 2020? So first off, 2020, subtract 1984, well, that's 36 years. So f of 36 would be the 75,000 times e. E is the natural function, natural exponential function. And then we want the 0.018 times the 36 years. Note that this part is not very big. It's not quite 2%. And then, so not quite 2% growth there. And then, so that's going to give us 75,000 times e to the 0.648. So f of 36 will equal 75,000 times 1.912, which gives us 143,378.5. So f of 36 years, we went from 75,000 to almost 150,000, so we almost doubled it. So that kind of shows you how the natural exponential function works. Even with this very small number of 0.648, we were almost at a point that every 36 years, maybe just slightly over 36 years, we would double our population. So there's the section on exponential functions.